Thank you guys for playing that game. When I played this game with my team, which was just me, I won 6 out of the times that I played. Holler. Which means I have found out that I had, based on my results of winning, I had a 6 out of 10 chance of winning, which is 0.6 or 60% chance. So I found the probability of winning this game based on my experience. Clearly, my experience might not have been yours. So can you do the same thing with your experience with your team? However many wins you got, give me the probability of winning based on your experience. But what we're going to do now is we're going to aggregate this data, which means I want to know the wins for each of the groups. So we're going to put this in this table so that we can see as a class how many wins we got. So let's fill in the table. So here's the wins for our entire class. How many wins total? You guys have calculators today. Can you total up the number of wins for the entire class? We have 42 entire wins for the class. So based on that percentage, now from the whole class, not just my experience, but the experience of the whole class, we can now see the probability of winning this game. There were 10, 20, 30, 40, 50, 60, 70, 80, 90, 100 trials that we did in this class because of the 10 groups. So we won 42 out of 100% of the time, which is 0.42 or 42%. Both of these probabilities that we just did, since they were based on an experiment, based on an experience that you had, these two probabilities are called empirical probabilities. They're empirical probabilities. But since an empirical probability is based on your experience, and the experience still has chance in it, and we have variability, some people only won 3 times, some people won 6 times. In my last class, somebody won 8 times, and somebody else also only won 1 time. We have all this variability in our data, which means it's not necessarily the most accurate probability based on all options available. It's just based on experience. So how else could we improve this estimate of the probability of winning this game? What else could we do? Do more times, okay? Absolutely. We could do more trials. If I had every single one of you, all 27 of you plus me, so 28 of us do this 10 times, that'd be 280 trials. That's way more than 100. That will mean that we are employing what's called the law of large numbers to help us out, because the more times that we do it, the more often we have offset for the variability in people's wins and losses. So we'll get closer to the true probability. And in fact, if we were really trying to find the probability of this experiment of winning, we would want to do this mathematically. And if we figure it out mathematically, it's a different type of probability because we're not basing it on an experiment or basing it on our experiences. We're going to be basing it on mathematically what is as all possible for us to do. And the way that we do that is through the use of what's called a sample space. So to determine the true probability of winning, we can list out all possible pairs of choices that we could get. Again, this is called S, the sample space. Now, I don't know if you actually looked in the bags that I gave you, but dump them out for a second and tell me how many Starbursts are in there and what color they are. Riley definitely cheated. Tell me about these Starbursts. How many reds are there? How many yellows? Okay, so if we're making a sample space for every option of 2 grabs of Starburst, we could have the first grab be the red, the red, the red, the red, or the yellows. And then we put them back in, and then we grab them back out, which means our second grab can again be the 4 reds and the 2 yellows. So the sample space will now be created in like a little Punnett square situation. Yes, so if this row says R and this column says R, what would go in this box? R, what would go in this box right here? RY. Let's go ahead and fill in the entire sample space for literally all of the options that could have happened with our 2 grabs of these 6 different Starbursts. So red, 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 yellow, red, yellow. You get it, yes? I'll stop talking so we can fill this in. Here's what our sample space looks like. Again, this represents every singular option that could have happened when we reached in and pulled out and put back, reached in, pulled out. Okay, highlight the outcomes with both red, so winning basically with reds, in pink because I don't have red highlighter. So grab a pink highlighter and I want you to highlight all of the red reds. So this is all of the places we could have won by pulling a red first and pulling a red second. How many total possibilities from my sample space did I highlight pink? 16. So there were 16 out of the 36 options that I had that would allow me to win with red, red, which means I have a 16 out of 36 chance of winning red, red. And if we do 16 out of 36 in our calculator, you'd get 0.444, a whole bunch of fours, which would be 44.4%. So we have a 44% chance of winning this game by pulling 2 reds in a row. Now let's do the same thing because this was not the only way you could win. You could also win by pulling 2 yellows. So let's highlight the yellows that are winning yellows in yellow, if we will. How many of those did we fill in? There's only 4 of those that we could have won by winning yellow. 4 options. 4 out of 36. Toss that in a calculator. You get 0.111 or 11.1%. Now the sample space is helpful for us to find a different type of probability. Remember earlier, we did empirical probability when we were going off of our actual experiment. But question number 5 here asks us overall, what is the probability of winning? We can either win by red, red, or we can win by yellow, yellow. So what we would do is we would add the probability of winning by red, red with the probability of winning by yellow, yellow, or simply count up the number of things we highlighted, right? We highlighted in total 20 different things, which is 16 plus 4. We have the wins from the reds and the wins from the yellows. 20 out of 36 is our actual probability of winning, which is 0.555 or 55.5%. This type of probability, where we went through a sample space, saw all the possibility options that we could have, and then found the real probability, the actual probability based on chance, this kind of probability is called classical probability. And classical probability, when we can actually compute it, is very nice because it's not based on any experimental variation. It's based on legitimate options that you have, the real probability of this occurring. Next page, to discover how we can relate probabilities to each other, we're going to do another small little survey amongst the class. The survey is this. Some people think that the ability to do taco tongue and evil eyebrow is something that you're just born with. Is this true? Are these abilities somehow related? These are the sort of questions we could ask. Now, what is taco tongue, you're asking? This is taco tongue. Can you do taco tongue? Evil eyebrow, I actually cannot do evil eyebrow. It's the one where your eyebrow just like one eyebrow. Both my eyebrows move at the same time. I can't get just one move, so I can't do it. So here's what I need to know. For all of us here today, I need to know how many of us are yes to taco tongue and yes to evil eyebrow. Me personally, because I can only do taco tongue and I cannot do evil eyebrow, I'm going to put a tally mark for myself where it says yes taco tongue, no evil eye. You don't have to show me, just assess for yourself. Can you do it? Take a second. Okay, so we've tallied up our class, which means that for our yes, yes, being able to do both, there were 10 people in class who could do both. There were 9 people who could do taco tongue but not evil eye. There were no people who could not do taco tongue but could do evil eyebrow. And there were, 8 people who could not do either. So question for you, how many people in total for class can do taco tongue, period? How many people can do taco tongue? How'd you get 19? Nice. How many people are no taco tongues? 8. How many people are yes to the evil eyebrow? And how many people are no to the evil eyebrow? 17. Which means grand total, how many people do we have in our class? 27. We can get it by either adding the rows or adding the column for the totals. This is called a two-way table. It's called a two-way table. You're showing me two different things and totaling them up separately. This is going to come back to haunt us in a couple lessons, but it's called a two-way table. It'll come back to haunt us in a couple lessons. We're going to use them again in a couple lessons. That's another way to say that. Now, I find it way easier in general to do probabilities in Venn diagrams, because Venn diagrams show me circles for yeses and an overlap for where they both occur. So if I were to put our numbers from here into my Venn diagram, the number of people who were yes to both would go in the overlap of the Venn diagram, which means I'd put 10 right here. There were 10 people who could do both. So they go in both Venn diagrams. The number of people who were yes taco tongue but no evil eye would go in the just yes taco tongue section, so 9 goes here. There were none that could do evil eyebrow that couldn't also do the taco tongue, so this is 0. And this Venn diagram isn't just the two circles overlapped. My entire sample space is the rectangle containing the Venn diagrams, which means my 8 people who couldn't do either of them, you get to be on the outside. You're still included. You're in the rectangle. But you're on the outside of the abilities, but you're still in sample space. Here's what's cool here too. We said there's a total of 19 people who could do taco tongue, and if you add up the two numbers inside the entire circle, it's still 19. So this still has all of the information from my two-way table, it's just in a Venn diagram form. That is super helpful for us when we get into some of our probabilities later in class. But let's find all of the probabilities. Since we randomly choose a student from class, what is the probability that that person would be a yes to the taco tongue? And we're just going to leave these answers as fractions today because I know you can put them in the calculator, change them to decimals and percents. We're going to leave them as fractions. So yes, taco tongue. How many people were a taco tongue for us? I have to zoom out because I cannot see. There were 19 out of the 27 people in class were yes to taco tongue. How about yes to evil eyebrow? How many people total? 10 out of the 27 in class. How about no to taco tongue? 0 out of the 27 in class. And no to evil eyebrow? Wait, sorry, that's 8. Hee hee. I was testing you. And how about no to evil eyebrow? 17. So probabilities are super simple. It's the frequency of what you're looking for out of the total number of trials, right? Our trials is the number of people in class. You guys are all part of the trial. If we're looking for the no taco tongues, there were 8 of you out of the 27, that becomes our probability. We put it in a calculator, make it a decimal, make it to a percent. Easy peasy. But then we start introducing these interesting symbols. Does anybody know what this symbol means? It's the and symbol. In set notation, this is and. You know how when we did interval notation in college algebra and we did the parentheses or the brackets with a U in the middle? What was that word? Union. What did it stand for in math though? If this is the word and, it stood for the word or. So the word and or are set notation, but this is and. You might want to write that down because I don't think it's notated anywhere. When you see the one that looks like an N, it's and that's how I always remember it because the word and literally has the symbol in it. So that's how I've always remembered it. Okay, for this probability, we were wanting to know the probability that we randomly select someone that is both yes to taco tongue and yes to evil eyebrow. How many people were yes taco tongue, yes evil eyebrow? 10. That's 10 out of our 27 people because we want the overlap between those two things. How many people were no taco tongue and yes evil eyebrow? No taco tongue, yes evil eyebrow. 0 out of the 27 people in class. How about yes to taco tongue, no to evil eyebrow? 9 out of the 27 people in class. No taco tongue and no evil eyebrow. 8 out of the 27. Again, most of the times you won't answer probabilities in fractions. I know where I'm going with this lesson today, so I want them as fractions. Your homework will want them decimals, usually rounded to 3 or 4 decimals, but read the question because it changes per question. Now we can start answering more complicated questions. Okay, I'm not going to be able to show you both because of the way the screen is, so make sure you're looking back at those numbers this whole time. In fact, let me take a picture of it so that I can look at the numbers at all times. Okay. Find each of the following probabilities. 2 of these we've already done, so it's just copy paste. What was the probability of yes, evil eyebrow? How many people could do evil eyebrow total? 10 out of 27. Okay, how many people were no to evil eyebrow? 17 out of 27. So a new symbol has appeared. You guys know this one though. This is the or symbol. When in probabilities, when I see the word or, my brain needs to start thinking add. Because if we're looking for this quality or this quality, we're going to add those probabilities together to add together the probabilities of finding this or that, the 2 different qualities that are options for this event. So if I find the probability of evil eyebrow, which was 10 out of 27, and no evil eyebrow, which was 17 out of 27, I'm adding them together. When I add together 10 over 27 and 17 over 27, what do you get? 27 over 27. Wait a second. That's 100%. Does that make sense in this situation? Think about what I'm asking you. What is the probability I pick somebody out of class that either cannot do evil eyebrow or can do evil eyebrow? Those were the only 2 options I gave you, right? There was no like sort of do evil eyebrow. It was either yes or no. Which means one of those 2 options is literally everybody in class. So I have a 100% chance of picking somebody out of this class that either can do evil eyebrow or cannot do evil eyebrow. That makes sense. Let's do number 4. Number 4, we're again copy pasting these numbers down for ourselves. What is the probability that somebody can do taco tongue? 19 out of 27. How about yes to evil eyebrow? 10 out of 27. Okay. So I start to add these together because again, the last probability says yes taco tongue or yes evil eyebrow, and that's my indicator to add. So I go to do 19 over 27 plus 10 over 27, and what do you get? Whoa, your spidey senses should be going off because 29 over 27, what do you know about that? That's over 100%. Is it possible for me to have a probability that's over 100%? No. 100% is like that it is certain, that it is going to happen. 27 out of 27 means everybody in class is accounted for. I can't invent 2 invisible people. No, you can't just be making sure. This should, if you ever get a probability that's like above 1, you need to pause because something's wrong. What's wrong with this? What did we do wrong? What? I'm double dipping. Tell me more. What do you mean? I'm counting for people twice. Tell me more. Like what people? Oh, the people who can do taco tongue and evil eyebrow. What's the symbol for and? The N thing, yes, okay. So what I'm hearing is that when we add these 2 numbers together, what do we want to do with that and statement, with the overlap? Well, I'm adding the 2 probabilities together and it's too big. Subtract. My friends, if we're actually trying to find this, we're going to add the taco tongue, which is 19 over 27. We're going to add the yes evil eyebrow, which was 10 out of 27. But we have to subtract the people I'm double dipping, I'm double counting. How many people could do both? Yes taco tongue and yes evil eyebrow? How many people were yes to both? I actually don't remember. Is that the right number? 10? I was pausing because I couldn't remember what our numbers were in this class. Which means that we would actually have 19 out of 27 people in this probability. Now, the reason I brought up both of these examples, number 1, because we make sure that we have to, if we are double dipping, that we are subtracting out this overlap. That's what we're going to informally call it. That we have to subtract it away. Now, we didn't have to do that. We didn't have to do that in the first problem, in question number 3. Why did I not have to subtract away an overlap in number 3, but I did in number 4? It was right exact 100%. Tell me more. It didn't overlap. If there is no overlap in the two things, the two traits you are trying to find the or probability for, that means that they are called two mutually exclusive events. They are mutually exclusive. If you're Googling around for other words, you might also see the word disjoint. That means that they are mutually exclusive. They do not join together, they are disjoint. Or they are exclusive to each other, mutually exclusive. However, when there is an overlap, this sort of problem was because this is not disjoint or not mutually exclusive. So we do have to be paying attention when we do these or statements as to whether our two traits have any sort of overlap, meaning they are disjoint or not disjoint. Because if they are not disjoint, we have to subtract away the overlap. This page has a lot of the vocabulary I've already kind of talked with you. I'm going to hit some of the highlights. You can read the rest of them. I'm not going to hit all of them. Look at the rules of probability. We're going to go here. When you are making what's called a probability distribution, or listing out all of the probabilities for different options, there are two rules. The first rule makes sense. No single probability can be below 0 or bigger than 1. That makes sense, right? You can't have a negative probability, and you can't have a probability of 150%. They have to all be between 0 and 1. And in a probability distribution, the sum of the probabilities of all outcomes must add up to 1. All outcomes that are options, we have to have a 100% chance of all of the options occurring. So all the options added together have to be 1. The next vocabulary word we're going to skip down to is the unusual events. Again, in statistics, calling something unusual is like an actual vocabulary word, not just saying like, it's kind of unusual. This has a number associated with it, and it is still that 5% or 0.05. If your probability is less than that, your event is actually unusual by definition of statistics for unusual events.
It's less than 5%.
It's unusual. And then we have our two types of probability that we talked about. You have your empirical probability from an experiment and your trials, and we have classical probabilities where we have to find a sample space and count the number of items that are winning in that sample space versus existing in the sample space. That's what those two formulas are telling you. The last 3 things we're going to annotate on here. When, again, we're talking about disjoint or mutually exclusive events. We're talking about 2 events that have no outcomes in common. So let's draw a Venn diagram that shows disjoint events. If we have a Venn diagram, remember the rectangle that contains the Venn diagram is actually important. It's part of the sample space. A mutually exclusive set of events would be like a pink circle being here and a blue circle being here, and they don't overlap at all. No, I'm going to leave that. Disjoint events have no overlap. They have nothing in common. However, when we start working with not mutually exclusive events, we have to take them into account. So in our Venn diagram, which we've seen earlier, let's say for 2 non-disjoint events, we have the probability of E, and we have the probability of F. Notice that when I highlight both of them and they overlap, doesn't it change colors? Theoretically it should. It might just turn into a blob on your paper. But this middle part right here, if I'm using pink and blue, that makes purple. We have to not double count that purple section. So our general addition rule says that for OR statements, we find the probability of OR statements by adding the probability of one part of the Venn diagram, the probability of the second part of the Venn diagram, and subtracting away the overlap. Because we've double dipped, we've double counted the overlap if we don't take them away. in statistics, a complement is the parts of the sample space that are not a part of the given event. This is how you write a complement. It looks like an exponent and it's just a C. It's pronounced E complement. You can find the probability of E complement by doing 1 minus the probability of E. Because if E is the event, E complement is literally everything else. So you take 100% and you take away that probability. You get this constant. Visually, in a Venn diagram, this is how you draw a complement. Here's my Venn diagram. Here's my event E. Everything outside of that pink circle is E complement. So if the entire universe, the entire sample space is 100%, and you just want the stuff outside of the Venn diagram, you take 100% and you subtract the pink circle, you would get all the leftovers. That's the idea of complements. Sometimes it is super helpful to use a complement instead of a regular probability to find out the probability you care about, because complements might be subtracting one thing as opposed to adding a bunch of things. You'll see that next time. Now this last little bit down here is just a reference for you. I taught this class before and I was kind of shocked that I guess we're in different generations, but I grew up playing lots of card games. And when I gave an example with a card game in the last couple of years, a lot of people didn't know what a standard deck of cards looks like. This is what a standard deck of cards looks like. So if the question asks you something about a standard 52 card deck, this is what it's talking about, where you can see there are 13 spades, 13 hearts, 13 clubs, 13 diamonds. 4 of each type of card, 1 in each suit. You can see the number of face cards, unless you're counting ace as a face card. And you can see all of the number cards. I also have provided you with the sample space for rolling 2 fair die, like rolling a 6-sided die and then rolling another 6-sided die. You can get a 1 the first time and a 1 the second time. You could get a 3 the first time and a 4 the second time. That's what this is showing you. These are just references for you because I know that the homework references different games of chance. And if you don't play cards, you may not have known what kind of cards were in a deck. So you can just use this image. Also, play more card games. They're fun. Let's do some practice problems. This first question says, for sample space A, B, C, D, E, F, G, H, I, J, there are 2 events. Event E is getting the letters A, B, C, D, and E. Event F is getting the letters A, E, and I. Before we do anything else, let's draw a Venn diagram that shows this sample space. Okay, so we start with the rectangle that represents the entire universe here, the entire sample space. We will have E, we will have F. Okay, inside of the E circle, I need to make sure the letters A, B, C, D, and E are represented. And then inside of the F circle, I need A, E, and I represented. But I notice that some of those letters are the same for both E and F, correct? What 2 letters are in both event E and F? A and E. So I'm going to put A and E in the overlap because they are in both events. Now, I need to fit the rest of the letters in event E in that pink circle. So what other letters can go in the pink circle? B, C, and D. Because notice, inside the pink circle totally is still A, B, C, D, and E. What letter can go over here? I. Because then inside the blue circle is still A, E, and I. It's just showing that we have an overlap of A and E. But that's not every letter from my sample space. S is the sample space. What letters am I missing? F, G, H, and J. These are still a part of the sample space, but they are not in E and they are not in F. So they go on the outside here. Now we can start to answer the questions for this problem. The first question says, are events E and F mutually exclusive? That's a yes or no question. Why not? There is stuff in the overlap, correct? So this answer is nope, because A and E are in both, meaning they have an overlap. So they are not mutually exclusive. They are not disjoint. But the Venn diagram will very much help me answer the next three questions. The probability of E and F, that is the overlap. How many letters are in my overlap? 2 out of how many letters in the total sample space? 10, which means this is a 20% chance that I would pull out of sample space S something in E or F. Sorry, E and F. Speaking of or though, part C is my or statement. This is the one that requires us to do a little bit of work. The formula is add the probability of E, add the probability of F, subtract the overlap. Let's do that. What is the probability of E? How many letters are in E? And why is it 5? But I'm counting the overlap. Like, I want all of E. How many letters are in F? 3. Now I'm taking away the overlap. How many letters are in the overlap? 5 plus 3 is 8. 8 minus 2 is 6. This is 6 out of 10, or a 60% chance of us picking something in E or F. The last one says find the probability of E complement, meaning I want to know the probability of everything except for stuff in E. The formula for complements is 1 minus the probability not complemented, meaning the probability of E. We've already found this probability though. What is the probability of E? There were 5 options out of the 10 contained in E. 1 minus 5 over 10 is still just 5 over 10. So there's a 50% chance I find E complement. And here's why Venn diagrams are really helpful. E complement means everything outside of the pink circle. How many things are outside of the pink circle? Is this in the pink circle? So 1, 2, 3, 4, 5 things are outside of the pink circle, right? 5 out of 10, 50%. If it had asked, what is E or F complement, that would be 4, because that means not inside the blue or the pink circle. That's what you guys were thinking. Questions, comments, concerns? That would be this complement, because there was 4 things not in either of the circles. Is the middle stuff inside of either one of the circles? It does. Number 2, for 2 disjoint events, A and B, we know that the probability of A is 0.25 and the probability of A or B is 0.65. Immediately, that's all we're given. The first part says, what is the probability of grabbing A and B? A and B. Here's your hint. What does it mean for something to be disjoint? There's nothing in common. So what is the probability if I get something that's in A and B? 0. There's nothing in common. Disjoint means there is nothing in common. So it's 0. Disjoint means nothing that is in common. Second question wants me to find the probability of B. The only information I'm given is information about the probability of A and information about the probability of their union of A or B. So I have to think to myself, how can I relate all of these things together? And it comes from the formula that's on the back page here from our addition rule. that says the probability of A plus the probability of B minus the probability of the intersection should be equal to the probability of the union. That's straight up the formula from the back page. It's on your formula chart. This is what you guys figured out when you're like, can't double count the overlap. That's the formula right here. Let's fill in what we know. Do we know the probability of A? What is it? 0.25. Do we know the probability of B? No, that's what we're trying to find out. Do we know the probability of A and B? We do, because they're disjoint. Do they have anything in common? No, they have nothing in common. Do we know the probability of A or B? 0.65. My friends, once we fill in everything we know, we only have one variable left we can solve. Minusing 0 is kind of boring, so instead I'm going to subtract 0.25 from both sides so that the probability of B is isolated. 0.65 minus 0.25 is 0.40. Part C goes on and asks you, hey, but what if events A and B were not disjoint, meaning they had something in common? And in fact, it goes on to tell us, let's say that the intersection, the probability of the intersection is 0.10. What is the probability of B now? Well, close. You're on the right track. But if we actually plug this all back in, it's 0.25 plus the probability of B minus 0.10 equal to 0.65. And I know why you said 0.3, 0.5. So we would we'd have to combine our like terms first on the left side of this equation. This would end up being plus 0.15, because 0.25 minus 0.10 is 0.15. Then when we subtract it to the other side, 0.65 divided by 0.15, you get 0.50. Last example together kind of throws it back to something that we had in chapter 2. I've given you in this problem a frequency table, so like a tally marks, right, of the number of people. Well, I didn't ask. Somebody asked people, how do you get to work? And this is how a bunch of people responded with how they got to work. 83 people said they drive by themselves. 22 people said they carpool. 10 said they take public transportation. 5 said they walk. 3 said other. And 77 said that they work from home. In chapter 2, after we had a frequency distribution, we made what was called a relative frequency distribution. How did we do that? The relative frequency. No, not it. I want you to just tell me what are we doing if we're making a relative frequency? You're thinking too hard. Easier than that. We divide that number, the frequency, by the total number of things. In fact, a relative frequency distribution is actually a probability distribution. Because if we are finding the number of trials out of the total number of trials, which is empirical probability, that's what we're going to be doing in this table. So first thing I need to know is how many total people were surveyed for this survey. Please add those up. The total should be 200. Now, if I'm finding what was called the relative frequency distribution, which is still valid and is still a thing, but the probability distribution is found in the same way. If I'm finding the probability of somebody driving alone to work, what I'm going to be doing is 83 over 200. And I'm going to give it to me as a decimal rounded to 3 decimal places if we need it. So what is 83 out of 200? 0.415. I need you to fill out all the probability distribution here, which again is acting like a relative frequency distribution. And once you get all of these probability distribution, we want to check and make sure it actually follows the 2 rules of probability that we discussed. The first rule was that no singular probability is less than 0 or bigger than 1. Are we good? The second thing is that the sum of all the probabilities in a distribution must add up to 1. So I need you to add each of these probabilities real quick and make sure it sums to 1, just to make sure we didn't mess up anything. Are we good? Yeah. And that's good. And we did actually check the same thing when we did a relative frequency distribution. We did the same thing to make sure everything was accounted for. What proportion of the entire experiment was this response? That's a probability. That's an empirical probability. And once we have this probability distribution, we can answer questions like A, B, and C. It says, estimate the probability that a randomly selected individual carpools to work. What's the probability somebody carpools to work? 11%. So we could say 0.110, or we can say 11%. Nice. We didn't have to do extra work because it's in my distribution table. Part B goes on with that question, though. It goes, okay, well, for every 1,000 people that we survey, we should expect about blank number of people to carpool to work. When you're looking for this sort of expected value, you're going to be calculating the following. You will do the probability of the event multiplied by the number of people that you have surveyed. So for us, we would do 0.110 times 1,000, which is really just moving the decimal point 3 times. It should be 110 people that we're expecting to find that carpool to work, since the probability is 11% and we're surveying 1,000 people. Yes? That's value, expected value. Now, the last question right here says, would it be unusual to randomly select a person who walks to work? Remember that unusual is a very specific number. What was the number? 5%. What was the number of percentage of people who would walk to work? The answer here is yes, because 2.5% is less than 5%. 5% is our threshold for unusual, and since 0.025 is 2.5%, that is less than that number, it is considered to be unusual.